In this video, we're going to continue to talk about Newton's laws of motion. Specifically, this time we'll be introducing Newton's second law. Newton's second law answers the following question: what causes acceleration? So if we have an object and it's accelerating, what's causing that? What does the acceleration depend on? Newton determined that the acceleration is equal to the net force acting on the object divided by the mass of the object. So remember that net force from our previous video, we said by the net force we mean the vector sum of all forces acting on the object. So that's important. We have to add up all of the forces acting on the object, and because force is a vector, we have to do a vector sum. M then just stands for the mass of the object. So we can see that mathematically all this is telling us is that the acceleration is directly proportional to the net force and inversely proportional to the mass of the object. If you've learned Newton's second law before, you probably remember it this way. Usually we just say F equals ma. There are a couple things about that to just watch out for. First of all, it's not just any force. It's not F equals ma. It's F net equals ma. So it's important to remember we have to be talking about the net force. It's often convenient when we're solving problems to write Newton's second law in this way, and we'll often do that. But I wanted to write it first this way to emphasize the fact that force causes acceleration. And the larger the mass, the less acceleration there'll be for a given force. So remember that. Forces cause acceleration. Acceleration does not cause force. One of the things that you'll notice is that as soon as we write down Newton's second law, we realize we really don't need Newton's first law anymore, because in fact it's incorporated in Newton's second law. Newton's first law is simply a special case of Newton's second law. As we talked about in our previous video, if the net force acting on an object is zero, that means the object is not accelerating, and therefore the object is moving with a constant velocity, and of course that constant velocity could be zero. Okay, so Newton's first law, it's just a special case of Newton's second law. An object will stay at rest or stay moving with constant velocity unless there's a net force present. So no net force, no acceleration, constant velocity, or no velocity. Try the following question. What is the direction of the net force acting on a cannonball in projectile motion at the point shown? So here's where the cannonball is in its flight, so it's not yet at the ground, and I want to know, what do you think the direction is of the net force? Pause the video and come up with what you think is the best answer. It turns out that the correct answer is C. And there are a couple different ways we can see that. First of all, you'll notice that when I write the acceleration is equal to the net force divided by the mass, I'm putting a vector sign over both A and F because acceleration and net force are both vectors. Remember that when we multiply or divide by a scalar, we don't change the direction of the vector unless the scalar is negative. Well, mass can't be negative. So what you'll notice from this formula is that A, the acceleration, and the net force are always in the same direction. So that's important. Well, we already know what the direction of the acceleration is in projectile motion. It's straight down. In other words, we've said it's negative 9.8 meters per second squared. Notice that makes sense because in projectile motion, remember, we're saying we can ignore air resistance. The only force acting is the force of gravity. Well, that's also straight down. So the net force is straight down and the acceleration is straight down. Now, we said that A equals F net over m, or F net equals ma, is a vector equation. Let's talk about what we mean when we say we have a vector equation. What we really mean is simply that this equation has to be true for each component. In other words, if overall F net equals ma is true, then it has to be true for the x components. So the x component of the net force is equal to the mass times the acceleration in the x direction, y direction, and z direction if it's three-dimensional. Let's look at a quick example of that. Again, we just finished recently talking about projectile motion. And in that last example we looked at the object when it was somewhere over here. Think about what we know about projectile motion. There is no acceleration in the x direction, and the acceleration in the y direction is negative 9.8 meters per second squared. Well, that makes sense because the only force acting on this object once it's in projectile motion is the force of gravity, and that's negative and it's in the y direction. There is no force acting in the x direction, so it makes sense that the acceleration in the x direction is 0. Let's look at the units for force. Force is measured in newtons, and what we want to understand is how is a newton defined? The easiest way to look at questions like this related to units is to first write down the associated equation. So I'm going to write down Newton's second law. The way we define the newton then is that 1 newton is 1, and now we need to look at the units of mass and acceleration. Well, the units of mass are kilograms. The units of acceleration we know are meters per second squared. And so the definition of a newton is 1 newton is 1 kilogram meters per second squared. Let's answer the following question. What forces are acting on my coffee cup? So here we have a table, and let's say that my coffee cup is sitting here on the table. What forces are acting on it? Well, I think we know of one for sure, and that is the force of gravity. Let's see if we can figure out how to calculate the force of gravity in this example. In order to figure out how to calculate the force of gravity, we use a trick, and that is we know something about free fall. Remember, free fall just means an object that's falling under the influence of gravity where there are no other forces that are present. So in other words, we're neglecting air resistance. So imagine I've got an object that's falling and the only force acting is the force of gravity. Think about what else we know. We know that the acceleration in the y direction when I drop something is just equal to negative g. Let's apply Newton's second law and see if we can figure out what the force of gravity is equal to. We know the net force is equal to the mass times the acceleration. And here I'm going to put y subscripts because we're just interested in the y direction. Notice that the net force is just the vector sum of the forces, and that's just negative Fg because there's only one force, which is the force of gravity, and it's in the negative direction. We know that the object is going to accelerate at negative g, and so I'm going to plug that in for A. And what we get is the force of gravity is equal to mg. So just because we understand what happens when an object falls, we find that the force of gravity is just equal to m times the acceleration due to gravity. And that is the quick way to calculate the force of gravity or weight of an object. There's one really important thing you got to keep track of here. From now on, when you see little g in a formula, it doesn't mean that something is actually accelerating at 9.8 meters per second. Remember, whenever you see g with an m in front of it, it's just our shorthand way of calculating the weight based on free fall. So in other words, my cup here on the table is not falling, but if I want to calculate the force of gravity on it, I now know how to do it. I just take the mass of the cup and multiply by 9.8. By the way, there's a lot more to gravity than this. In a later video, we'll talk about the universal law of gravitation, and that's what we have to use if we're dealing with objects not right near the surface of the Earth. So for example, if we want to look at something like the force that the sun exerts on the Earth or the force the Earth exerts on the moon, in that case we need the universal law of gravitation, but I'll hold off on that for a later video. For now, when we want to calculate the force of gravity or weight of an object, that's all we need. All right, what other forces are acting on my coffee cup? Well, the other force that's acting on my coffee cup is what we call the normal force. The normal force is the force that a surface exerts. So clearly, just as the Earth is pulling down on my cup, which is the force of gravity, my cup's not falling, so there must be a force in the opposite direction. That's the normal force. The reason we call the force that a surface exerts a normal force comes from mathematics. In math, we use the word normal to mean perpendicular. What we're talking about here then is that the force that the table exerts up on my cup, which we're going to write as F subscript n for normal force, is perpendicular to the surface. So that's why we call it the normal force. Now, let's say that my coffee cup is on an incline. Well, in this case, again, the normal force that that surface exerts is always normal to the surface. So that's our right angle. What you'll notice here is that if we draw in the other forces acting, which is the force of gravity, right? So the cup has a force of gravity acting down on it here. You'll notice that the reason the cup doesn't move in this case is because the net force is 0. The normal force pushes up just as hard as the force of gravity pulls down. But notice over in this situation, the force of gravity is straight down. And therefore, that object is going to move because those two vectors can't cancel out. Now you might say, well, it doesn't have to move, and you're right, but that would be because there's a third force, which would be the force of friction. If there's enough friction between the cup and the incline, then those three vectors together can add to 0. If there's no friction or not enough friction, then there would be a net force down the incline and the object would slide down. Let's look at a simple example. A block is pulled along a table with a force of 5 newtons at a constant velocity. What forces are acting on the block, and what is the force of friction between the block and the table? One of the things that you always want to watch out for in a physics problem are the key phrases. And here the key phrase is constant velocity. So we've got to make sure that we don't miss that. Let's first draw a picture of what's going on. So I've got my block sitting on the surface. It's a block of mass m. And the block is being pulled along the table. When we have a force like that that's being applied, we call it an applied force, and we use F subscript A to represent that force. Let's draw the free body diagram. Remember that a free body diagram is a diagram of all of the forces acting on the object. We use a dot to represent the object, and now we simply go ahead and identify all of the forces acting. You might try it on your own. Well, the first force that we really always have is the force of gravity. We can't shut that off. The table is going to be exerting a force up. Remember, that's called the normal force because it's perpendicular to the surface. We've got our applied force acting to the right. And then we also have the force of friction. And at this point, we're going to use Fk to represent the force of friction. We'll see why we use K in a later video. But for now, just know that when we have sliding friction, where the object is actually sliding along the table, we label that Fk. That's my free body diagram. So I have identified all of the forces acting. The next step that we do in problems involving Newton's second law is we write down Newton's second law for each component that is relevant to the problem. So in this case, we have both the x component and the y component. I'm going to write F net x, that represents the net force in the x direction, is equal to max, where ax is the acceleration in the x direction, and F net y equals may. Let's start out by looking at the x direction. By net force, remember, I mean the vector sum of the forces. Now, when we do force problems, pay attention to this statement. All of our force symbols represent magnitudes. What I mean by that is they're always going to be positive if you solve for them. We're going to put in the direction of the force manually. Here's what I mean by that. Looking at our free body diagram, we can see that in the x direction, there are two forces, an applied force and a force of friction. The applied force is to the right, so I'll write that as positive Fa. The force of friction is to the left. I'll write it as negative Fk. So I put in the direction, and therefore if I finally solve for Fk, it's going to be positive because Fk represents the magnitude of the force. That's equal to max. Now remember, there's a key phrase in this question. The block is moving with a constant velocity, and therefore the acceleration is equal to 0. What I conclude then is that the force of friction is equal to the applied force. Again, notice these symbols represent magnitudes. So Fk, the magnitude of the force of friction, is 5 newtons because it's the same as the magnitude of the applied force. Let's look at what's going on in the y direction. We have two forces, the normal force and the force of gravity. The normal force is up, gravity is down. So I'll write Fn minus Fg for the net force. Now, what's going on in terms of the acceleration? Is this object accelerating in the y direction? Well, the answer to that is no. It's not going down through the table or leaping off the table. So that's 0. And in this case, then what I learn is that the normal force and the force of gravity have the same magnitude. Or the normal force would just be equal to mg, since remember that's what the force of gravity is equal to. Notice, because this object is moving with constant velocity, the net force has to be 0. And so that means both the net force in the x direction and the y direction are 0. In our next video, we'll talk about Newton's third law of motion.